Always had this one question in our life where we've doubted our education system and why we are actually learning all of this. To be frank, what are you going to do with a function which has variables? Like, what are variables? What are functions? Why is this going to be of any use in our life, right? But let me explain to you that this is all actually very important. As useless as you think calculus is, or for that matter, anything that you have studied in math is, it's not. Because come to think of it, everything can be put in math, and major philosophers have always said stuff like there is no world without math and everything around you is mathematically viable, which means everything can be proved by math. So math is the backbone of our existence itself. And let me explain that to you, because today let's just assume you work for a production company, and the production company now has two factors all the time: cost implementation and how many resources they have to be implemented, right? So now with these two factors, you need to maximize profits and minimize resources, and that can be done with the use of multivariable calculus, maxima and minima. As useless as you think this concept is, I will explain it to you on paper in a few minutes, but let me just explain the gist of these things. So we have two variables obviously, and we are plotting the cost variable as a function and the resource variable as a function, and now using the steps that are used to solve the maxima and minima to get the maximum point and the minimum point, we use those concepts to get the maximum and minimum point, and hence make a successful production company. I mentioned earlier in the video, I was going to explain the real life concept on paper. So as you can see, you're probably wondering what's on the paper. Because of a lack of a proper classroom that I did look for, and a lack of a chart paper that I couldn't find anywhere because it was a Sunday, I am forced to do it on a paper, and I'm extremely sorry for that. But I will make sure at the end of the video you get complete concept clarity of what I'm trying to explain. Okay, so first of all, my function is Q is equal to, Q is the Lagrangian function. This is a production function proportional minus proportional quantity of the budget constraint. So the budget constraint is this: 108 minus 3k minus 4l, and this is the Lagrangian function, k to the power 0.4, l to the power 0.5. You're probably wondering what k and l are. Yeah, they are random variables, but k is the price of capital. That is the opportunity cost of the objective function, and L is the price of labor. Okay, so I will now start explaining this concept to you. So now what the first step to finding the maxima and minima is to partially differentiate the function with respect to the variables individually. That is partial differentiation. That is the first concept we will be indulging ourselves into today. So as you can see, the function is k to the power 0.4 into L to the power 0.5 plus lambda times 108 minus 3k minus 4l. Now, a major doubt occurs: how do you differentiate such a function? It's simple. You just partially differentiate with respect to the variable k, and we don't use dq by dt here just like you do in normal integration, but we use dou q by dou x. Dou is the Greek alphabet, and I'm not going to go to the origins of that because I need to explain the video mathematically, and I'm just saying this so I can extend the video to 10 minutes, because I don't know what I'm supposed to do for 10 minutes. I don't know why I'm saying all this, but okay, yeah, whatever. Del q by del k, dou q by dou k is equal to 0.4 into k, 0.4 to the power 0.4 minus 1 into L power 0.5. Got it? Okay, amazing. I'm assuming you say yes from the other side of the video. I'm breaking the fourth wall.
Yes,
okay,
sir.
yeah. So after we differentiate it partially, we get the function 0.4 k to the power minus 0.6 L to the power 0.5 minus 3 lambda is equal to 0. Similarly, you're supposed to equate the partial derivative to 0. Similarly, on partially differentiating it with respect to L, we get 0.5k to the power 0.4 into L to the power minus 0.5, because 0.5 minus 1 is equal to minus 0.5, minus 4 lambda is equal to 0. This is function 1, this is function 2. But let's not forget about the other objective function that we have. So that is also dou q by dou L is equal to 108 minus 3k minus 4l is equal to 0. This is the objective function that I had explained in the first place. The lambda is a constant here. Again, sorry for poor quality of the video, but yeah, okay, moving on. I will, you're probably wondering what I can do with these random equations on a page. Let me explain that to you. So now, if you divide equation 1 by equation 2, we get dou q by dou k by dou q by dou L is equal to 0.4 times k to the power minus 0.6 L to the power 0.5 by, as this is a constant that will go off, by 0.5 to the power, 0.5 times k to the power 0.4 L to the power minus 0.5, and this is equal to 3 lambda by 4 lambda. From this we get L is equal to 0.9375 k. Interesting, isn't it? Now, what if we substitute this into this? Now we can minimize this by substituting this, as this is the minimum value, because we are dividing two differential equations, and that is the procedure you're supposed to follow for finding the minima, because we're trying to minimize the objective function in this case. So moving on, after we get this value, we substitute the result in equation 3. This is equation 3. I forgot to mention it, I'm very sorry. So on substituting this equation, we get 4L plus 3K is equal to 108, but 4 into 0.9375K plus 3K is equal to 108. And I'm very sorry about, I'm very sorry as I'm not able to show the calculation, but let me use the calculator, be right back. Okay, yeah, so we get, on substituting the calculator, we get the value of K naught to be equal to 16. You can verify it with the calculator if you don't believe me, but I really hope that you do. Okay, fine. So after this, you're probably wondering, okay, what can you do with the value of K? What use is it? Let me tell you, this is not the end of the problem, because let's admit it, everything is not so easy in life. You need to work a little harder. So moving on, we get 4L plus 3 into 16 is equal to 108. Now we get the value of L naught, and that's equal to 15. Voila! Didn't see that coming, huh? Okay, now you're probably wondering, okay, you got the value of two equations, you just solved two equations, what's so great in that? Let me explain to you that if you didn't have calculus, none of this would be possible. And okay, let me summarize the solution for you. So basically what I'm trying to say is, we need to, can you pause the video? Yeah, okay, so as I mentioned, now we've gotten the value of K naught and L naught. So as I mentioned in the beginning of the question, K naught is for the capital and L naught is for labor. So here this is for capital and this is for labor. So now I am just going to tell you that these two are the variables that will optimize the original function, that is this Q is equal to K times this equation. And now on substituting this value, we get Q is equal to K naught times to the power 0.4 into L naught to the power 0.5, because we have already substituted for lambda and gotten the final equation. So on substituting these values, we get 16 to the power 0.4 into 15 to the power 0.5. I need to use my calculator, just a minute. The answer is 11.74. And this is a verified result. If you don't trust me, you can feel free to try it yourself. And you're possibly wondering whether this is actually true or not, because I might just appear as a random person trying to explain a concept through this thing. But let me tell you this, that a lot of people have done this in life before, and they are called math teachers. So this is the pause. You can see we have optimized the function to the value 11.74. You're probably wondering this value might not be true, but it is true. It's proved by calculus, and calculus is God. Let's just not forget that. And no other combination of labor and capital, given the budget constraint, can achieve the higher level of output. I will show you the calculation once more clearly so you can understand. So okay, I'll talk now. Just turn the camera at me. So yeah, I would like to conclude my video by saying calculus is not just limited to maximizing or minimizing the constraints of a problem. It's much multivariable calculus is also used for a lot more functions, like there are limits, continuity, which are used in a lot more functions. And let me explain to you that calculus is literally the most important component of engineering, and also architectural landscapes like the size of a building and the number of concrete you're allowed to use for it. Everything is based on maximum and minima. And I would like to thank the video taker of this video, Jay Sridhar, and my friends who are in this room not talking and cooperating with me while I'm taking this video. Yeah, so thanks.